Okay, so let's start the class. So today we will finish the discussion on putting distinct objects into non-distinct boxes. So we will have some wrapping up about this topic. And after that, we will talk about the distribution of non-distinct objects into non-distinct boxes. So the latter topic is actually because objects are the same. You can think of each object as the integer 1. And then you have a total of, let's say, n objects, and then you want to put it into non-distinct boxes. So it is like you want to cut the integer into a set of integers such that they add up to n. So we call this the integer partitioning problem. Okay, so for one, okay, so let us review. So last time we have talked about this Stirling number of the second kind. So SRN counts what? Counts the number of ways to put R balls into n boxes. The balls are distinct, the boxes are non-distinct, and we have one more requirement. Each box cannot be empty. Is that okay? So this is called SRN. Okay? Okay, now, so we have a couple of numbers there. And so today, let me define a new number, a new calculation. Let me define something called BR. BR counts the number of ways to distribute our objects into non-distinct boxes. So we don't specify how many boxes you can use. You can use 1, you can use 2, you can use 3. Okay, and then okay. Of course, we don't specify the number of boxes that you are going to use, but we do specify that each box should not be empty. Okay, because in that sense, if you have 1 million boxes and then all of them can be empty, then you have one way, and then you have 1 million and 1 box, and then all of them is empty, then you have another way. So we don't want to count these cases. So for instance. So for instance, let's say we have altogether, excuse me, let me close the door. Okay. So for instance, let's say we have 3 objects. Let's say we have A, B, and C. Okay. So one way is to put A, B, C in one box. So this is one way. So we have A, B, C in one box. So this is one way. Is that okay? And then we have another way that we are going to use 2 boxes. So that we put A, B here and C here. Is that okay? We have also another way of using 2 boxes. Let's say there is another way. Maybe this time we put AC together, and then we put B here. Is that okay? And then we may have a third way of using 2 boxes. That we put BC together and A separately. So this is another way, right? And then we can have one more way that uses, this time, exactly 3 boxes. We put A, B, C, each in one separate box. And these are the only ways. We should not be using 4 ways. We should not be using 5 ways, because that will create empty boxes. Okay? So we may either be using 1 box or 2 boxes or 3 boxes. And the total number of ways is 5. So in that sense, here, we will write down B3 is equal to 5. Is that okay? So how do we get the Bell number? So we call this the Bell number. So how do we get the Bell number? Very simple. Yes, yes. So to get the Bell number, we just add up all the numbers in the same row. Okay, so we have 1 here, 1 plus 1, 2, 1 plus 3 plus 1, 5, 1 plus 7 plus 6 plus 1, 15, and the last thing is like 40, 50, 52, something like this. Is that okay? Okay, so this is the so-called Bell number. Okay, now I will check your understanding soon, but first, let us do something really complicated. So we are going to find out an exponential generating function for the Bell number. Okay, let's see. Let's see. So let's get back a little bit of what we have discussed before. Let's get back to the time where we have n, let me see, let's say n distinct boxes. This time, let's get back to the case where we have distinct boxes. Is that okay? So boxes are distinct. And then we want to get an EGF to calculate the number of ways to distribute objects into the boxes. So that there is an extra condition with no empty boxes. So I have an extra condition with into non-empty boxes. So these are the keywords. So we have n distinct boxes, and each of the boxes has to be non-empty. And then we want to get an EGF to count the number of ways to distribute objects. So that, okay, if I'm distributing R objects, I want the coefficient of x to the power r equal to the number of ways divided by r factorial. Is that okay? Is that okay? So I want the coefficient to be equal to the number of ways divided by r factorial, so that if I get the coefficient of this EGF, I multiply with r factorial, I get the number of ways of distributing R objects into n non-distinct boxes. N distinct but non-empty boxes. Is that okay? So what's that? So we've done that before. So because if you still remember, if we fix the total number of objects to be R, let's say they are going to be R objects, then we can encode a particular distribution by using labels here, like maybe I'm going to put this into box 2, I'm going to put this into box 1, I may be putting this into box 2, box 3, box 4, box 1, something like this. Is that okay? So this will be a kind of a string, an R-digit string using the alphabet 1, 2, 3 up to n. And then for each character in the alphabet, we restrict that it must appear at least once. Okay, so this EGF is going to be the product of the EGF of each individual character, and then this will be equal to e to the power x minus 1 to the power n. Is that okay? Does that make sense? Okay. And then, okay, this turns out to be, so we can write this as summation of R is equal to 0 up to infinity x to the power r divided by r factorial times AR. Is that okay? Where AR is equal to the number of ways to distribute R objects into n non-empty empty distinct boxes. Is that okay? Is that okay? Good. So this we are talking about the case of n. So let me give a subscript of n here to represent. This is talking about n. So let's talk. Okay. So we can have AR1, we can have AR2, we can have AR3, and we can have ARN. So ARN specifies that we are putting up. So this is about the case where we have n boxes. And then we are going to put our objects. Is that okay? Good. And now, last time, we also have this relationship, ARN turns out to be equal to, so it is related to this SRN. So last time we have talked about, okay, if we know how the number of ways to put balls into distinct boxes, then we can find a way to count the number of ways to put balls into non-distinct boxes, right? So what should we do? We divide this by what? R factorial or n factorial? What do we do? The idea is we remove the labels of the boxes, right? So all the labels of the boxes are gone. Originally, there are n factorial ways to label the boxes. And when they are gone, we divide it by n factorial. So AR divided by n factorial is exactly SRN. Is that okay? So AR turns out to be n factorial times SRN. Is that okay? So I can now change this a little bit. So ARN is equal to n factorial times SRN. Is that okay? Okay. So ARN. But now, what we are interested for the Bell number, if you look at BR, BR is equal to what? BR is equal to SR1 plus SR2 plus SR3 plus ... right? Up to SRR, right? Does that make sense? Actually, you can add SRR plus 1 without any problem, because SRR plus 1, according to that table, is 0. We can add 0. So we can add it up with infinite number of times. So this is BR. Okay. Now tell me, what is so special about this thing? So let's have this e to the power x minus 1 divided by 1 factorial. Let's observe this new function. I add it by e to the power x minus 1 to the power 2 divided by 2 factorial. And then I add it with e to the power x minus 1 to the power 3 divided by 3 factorial, and so on. We add this. Let's call this function f. So this is f of x. My question. So what is my question? My question is, what is the coefficient of x to the power r in this fx? What is it? So I want to get the coefficient of x to the power r in fx, right? What is it? So to get the coefficient of x to the power r in here, we can get the coefficient of x to the power r here, plus the coefficient of x to the power r here, right? Plus the coefficient of x to the power r here, plus the coefficient of x to the power r here, right? Okay. So what is the coefficient of x to the power r? So there must be some, okay. It can go very far away, right? So let's say there is a term e to the power x minus 1 to the power n divided by n factorial. Okay. Okay, so what is the coefficient of x to the power r here? We have written down x e to the power x minus 1 to the power n. So this is that term, right? Right? And then, what is the coefficient of x to the power r in this term? What is it? This term, it will become what? What's that? Look at this term. We find out what is the coefficient of x to the power r there. So this is this one. But then we need to divide it by n factorial, right? So we get what? So we get SRn divided by r factorial. Is that okay? How about the previous term? The previous term, it would be SRn minus 1 divided by r factorial. Is that okay? Is that okay? So the first term will be SR1 divided by r factorial. The second term, SR2 divided by r factorial. Is that okay? Is that okay? And what's that? This is equal to the Bell number r divided by r factorial. Does that make sense? Is it? This is the Bell number BR. Because we add up all SR1, SR2, SR3 up to SR whatever. So that the numerator part must be BR. And bottom part, everyone is divided by r factorial. So it is BR divided by r factorial. Is that okay? If you are okay with this so far, could you please raise your hand? If you need a little bit more time, let me know. Yeah, please raise your hand. Okay. So first of all, let's focus on this term. How do we get this term? How do we come up with the coefficient of xr here? We use the relationship here. Because we have now expanded ex minus 1 to the power n. And then this one is already expanded in this form, that x to the power r must be multiplied with this thing, and this thing, right? So once we have these things, this will be the coefficient of x to the power r here. And the coefficient of x to the power r, when we divide this by n factorial, we just remove this n factorial part. So we get SRn divided by r factorial. Is that okay? Okay. Now, when we change this, let's say n becomes n minus 1. N minus 1. Then we will have the same thing here, except that we are going to multiply n minus 1 factorial here. So this time, if it is n minus 1, and if we divide it by n minus 1 factorial, we will get SR n minus 1 divided by r factorial. So we will see that the change in n only affects these terms. It will not affect the division by r factorial. So everything here that we can write down, it will be s something divided by r factorial. So when it is n, this is SRn. When this is the term before, it will be SR n minus 1. Is that okay? Now, because everything is divided by r factorial, so we can take out 1 over r factorial as a common factor. And what is remaining? Remaining is SR1 plus SR2 plus SR3 up to SRr, which will be the Bell number. But then we can add up more, because those terms with this value greater than r, they are just 0. So if we add them up all, so in the end, the top part must all be 0, 0, 0, 0. But it never minds, because we ensure that we have all the terms from SR1 up to SRr. Is that okay? So when we have all the terms, they add up to exactly BR. So this is BR over r factorial. So what does that mean? Now assume that this is BR over R factorial. Then this means what? This means that this fx, this whole fx, let me wipe this now. This whole fx is the EGF for B, for what? For B0, B1, B2. Actually, B0, you can define it to be 1. Okay, this is just for convenience. For this sequence, BR up to infinity. Is that okay? This is the EGF that we want to find. This is the EGF for the Bell numbers. Okay, and now this is in a very special form. This is something divided by 1 factorial plus something square divided by 2 factorial plus something cubed divided by 3 factorial. And what is that? This is going to be very strange. Okay, imagine this is called y, not xy. So we have y divided by 1 factorial, y squared divided by 2 factorial, y cubed divided by 3 factorial. Then this will be e to the power y minus 1. We don't have the constant term. So this will be e to the power y. This is the y. Very strange. And then minus 1. Okay, that's it. So the EGF for the Bell number is very strange, but it can be written down compactly like this. Okay? Okay, now I have a question for you. Okay. So we just mentioned that this ARN, which is the number of ways to put R distinct objects into n non-empty distinct boxes. Right? So we have defined this ARN here. And then we argue that this ARN is divisible by n factorial. We talk about this. Reason: distinct becomes non-distinct, so it is like removing the labels, and there are n factorial ways to do the labeling, so we can divide this by n factorial. Is that okay? Now let me change a little bit. This time, let's don't consider AR. We consider something different. Let's remove the condition that the box has to be non-empty. We just assume that there are going to be n boxes to use. Okay, so we can still count the number of ways, right? So we have n distinct boxes. We have R items to put inside. Is that okay? So we get a new number of ways. My question is it still divisible by n factorial in general? No. Let's try an example, okay?